So we're going to begin part two with a look at the actual circuit diagram that we're going to be working with here on the unit. The circuitry that we were building in part one is the power supply unit, which is board number one, which is this unit here. And some of you may have already questioned why we have an integrated circuit. Why is there a PIC on a vacuum tube amplifier? Why do we have two FETs on a vacuum tube amplifier? The reason for that is because vacuum tubes require high voltage to operate, several hundred volts for the plates. And this unit operates off of 12 volts. There's our DC input right up here. So the circuitry that we were building yesterday all is part of the power supply unit to operate the high voltage generating power supply. And it's basically an inverter. And what they've done here is they've just used a standard PIC that they've programmed, and that PIC has been programmed to control the field effect transistors, the FETs. There are three of them. One of them is gated for the filament circuit, and the other ones are gated to drive the primary of the transformer. And how it works, if we look down here, our 12 volts comes in, 12 volts plus here. This is our 12 volt rail. And as you'll see here, our 12 volt rail is connected to our transformer. I'm just going to grab a highlighter so I can highlight this so you guys can see how it works. This will have to do because it's not in very good shape. I have two of them. So our 12 volts comes in. Here's our 12 volt line here. Our 12 volts comes in and supplies 12 volts to the power switch. The power switch controls the 5 volt regulator. That controls our PIC, which runs on 5 volts. The 12 volt line unswitched also comes down through ferrite bead number one. It charges up this capacitor here, C15, and it goes to the center tap of our transformer. That supplies 12 volts to the primary of our dual winding high voltage transformer. The other side of the primary coils go into our FETs. The FETs are controlled from two of the outputs. From the PIC. So when power is applied to the PIC starts to switch back and forth between the two outputs here on pin 15 and pin 16. So they're never high at the same time. One is gated on while the other one's off, and vice versa. So what happens is these provide, of course, a path back to ground. This is our ground here. So when the transistor turns on, when the FET turns on, it provides a path through the coil, through the one side of the primary, into ground, which produces a magnetic field on the transformer core. And then that transistor switches off, and as that magnetic field collapses, it induces a voltage onto the secondary. But as soon as that FET turns off, the other FET is going to turn on, which now draws our 12 volt supply in the opposite direction. So what we end up with is a magnet that is switching from north to south. We're creating an AC, an alternating current, or an alternating magnetic field. Another way of doing it would be just to cycle one transistor on and off, and then you'd have a fixed magnetic field that is turning on and then collapsing, turning on and then collapsing. This way you have two magnetic fields. You have a north when one is energized, and then when that one switches off and the other switches on, you've now draw a current the opposite direction. You create a south field. So this gives us a full wave AC waveform. And it would typically be a square wave, not a sine wave. It could be they could even make it a modified sine wave by adding a slight delay from when one turns off until the other turns on. But typically they just oscillate back and forth and create a square wave. That gives us our high voltage here, which is induced in the secondary stage, or rectified by our D1 through D4 rectifiers, and that gives us our B plus. You'll notice it's got a 22 microfarad 350 volt capacitor here. So that gives you an idea what type of voltage that we're dealing with. You guys can probably see it better than me, but it's 220 volts that we get from the secondary of our power supply, which is then handed off to board number 2, right, unit number 2, which is our tube amplifier. What that voltage does is that voltage is now applied to the B plus input of our 2 output transformer, the primary side of those transformers. So the voltage then, get my highlighter out again, our 220 volts, which is now rectified through the diode block here, goes over and it goes into our primary here, and it also goes over on this other leg here, over to this primary and through the primary. From here, it goes back and it goes into the plate of the audio output of the tube. How a vacuum tube operates is your high voltage is applied to your plate. Your grids here are what controls the flow of current. The cathode, which is pin 7, pin 7 and pin 4, I think it is for the triode side. We have a pentrode, which is a 3 screen cathode and plate, so 5 element, and a triode, which is a 3 element, which has got 1 screen and a cathode and an anode. So we've got a control grid. One of the control grids in a pentrode is connected to ground. That's to control leakage, and it's biased through pin number 8, which gives you your bias voltage. And what that basically does is it controls the amount of current that is going to flow through that tube. There's always going to be some current flowing through this tube because it's a Class A amplifier as opposed to a Class B, which would have 2 outputs, which is also called a push-pull. A Class A is always going to have some type of current flowing, even when there's no sound, and that is what this other control grid does here, is just provides a bias to create some electron flow from the cathode to the anode. So basically your cathode is heated by the filament and it's emitting electrons, and some of those electrons are being allowed to make it to the plate and complete the circuit. So we've always got a bit of DC current flowing through the transformer. On a Class A amplifier, you're always going to have some current flowing. That's why these amplifiers are all relatively low power, because if you had too much power flowing through here, you'd actually burn up the tube. So it limits the amount of current that is permitted to flow. As your audio signal is applied, and that's going to come in through, I think it's pin number 8, yes, because it's coming off of the plate of the triode side of the tube. The audio signal is going to modulate the flow of electrons coming off of the cathode. And as the voltage becomes more negative on pin 8, it is going to actually reduce the number of electrons, which will reduce the current flowing through the tube. And as it goes to a positive side of the waveform, is going to increase the electrons. So it's going to allow more current to flow through the tube. And electrons actually travel from the cathode to the anode, but the current goes the other way. So in effect, as you increase your electron flow through the vacuum tube here, you decrease the voltage on pin 6. So that causes, and that's where you get your amplification value, that causes the plate to do the opposite of what's on pin 8. So as the voltage rises on pin 8, the voltage goes down on pin 6. That fluctuation creates a fluctuating magnetic field in the output transformer, and of course the secondary is coupled to your speaker, and that's where your speaker is connected. That's basically how a vacuum tube operates. Now, there is a third FET, in the circuit, and it's over here. And it's also controlled from this PIC. It's controlled from another output on the PIC. These tubes are rated at 14 volts. The filaments are in series with each other, so you need 14 volts for the filaments. And that's for a PCL86. But if you replace it with an ECL86, here, there's a little switch that we're going to install. There's the jumper, or jumpers. Is it jumper or switch? Anyway, this transistor is gated from the IC to control the voltage going through the filaments. You can see it right here. One side's grounded here, right in the filaments. Or maybe that's just to turn the filaments off. Interesting. I have to look at that. Have to look at that some more. That may just be operating as a switch to turn the filaments off. They may not be gating the filaments on and off. I was thinking initially, looking at it, that they might be pulsing the filaments, and they change the duty cycle to change the voltage. But now looking at this jumpering over here, this here may change the voltage. FET3 controls the filament heater control, which would just be on or off. Anyway, I'm just learning this at the same time you guys are. This is the first time I've looked at the schematic. Anyway, that's the basics on how a tube amp works. So anyway, we're going to get back down to building unit number 1 here. This is part 2 of the video. So let's continue and mount some more parts. So step number 9 over here, we have to mount the DC jack. So there's the DC jack there. We'll mount, it's listed as jack number 4, which is right over here on our little circuit board. So let's mount jack number 4. And we'll solder that down. My roll of solder is starting to really get low. I hope I have enough to finish this project. Next, we have the speaker terminals to mount. So the speaker terminals just slide in like that, and they're soldered directly down to the board. So I'm going to tack it in place first. I'll tack one of them in place first, and then I'll go and solder the rest of them in. So this is just to hold it down. And now I can solder the other leads. Okay, speaker terminals are now soldered down. And that's step number 10. And step number 11 will be mounting the transformer onto this board. Actually, this has got, I think there's 3 transformers that go on this. Yes. This one's going to be the high voltage transformer, which goes here. And then we have our 2 speaker transformers. So let me locate the transformers. They should be back in the box. Here's one of the transformers here. It's all wrapped up. This one will be the high voltage transformer to power the vacuum tubes. And it only goes in one way. It's keyed. There's 4 pins on one. Here's our center tap here. These 2, so there's 2 separate windings. There's one of our primary windings there on these 2 pins, and there's our other primary winding. And this one here is going to be our secondary. So we put the transformer on the board and drop it in place, turn the board over, and solder the transformer in place. Smoke. Don't want the smoke in my face. So there's our power transformer installed. Next we have capacitors C14, 22, 19, 20, 11, 12, 13, and 15 to install. We'll start with C14 and 22, which are 120 microfarad electrolytics, so I gotta find them. 120 at 20 volts. It's these ones here, these little metal top ones that actually almost look like they're surface mounted, but they're actually not. But they look like they are. They look like the same type of aluminum can, but they're actually got leads on them. So it's these two ones here. These are 120 at 20 volts. So that's C14 and C22. So let's mount C14 and C22. Gonna find where they go. C22 goes over here. And where does C14 go? And C14 goes right down here between the two FETs. These ones are electrolytics. They are polarized, so you gotta be careful for your polarity. The negative is marked with a band or strip on them. And you can also tell the negatives because the leads are shorter. See the lead length here. The positive is the longer lead. So we'll mount these two capacitors down onto the board. These are 120 microfarads at 20 volts, which is an oddball voltage. You don't hear of that, and there must be a reason that they chose that. I mean, obviously they're in the 12 volt supply, but why that specific size and why that specific rating? They obviously had a reason for choosing that. And my solder is getting really low now. I might be running out. Wouldn't that be terrible? To not be able to finish this kit with the good quality Kester solder that I've had. This roll again is probably 30 years old. And it's still as good as new. Have no fear, I do have more. I do have another roll, but it's fine gauge stuff. So I don't really want to use that until this one's used up. Okay, we'll clip our leads off here. Using our Klein snips, and check off the C14 and C22, and then we'll move down to C19 and C20, which are 220 microfarad capacitors at 16 volts, which are these ones here. 220 at 16 for C19 and C20. C20 and C19 right here on both sides of the 5 volt regulator. Again, these are polarized capacitors. So the longer lead is the positive, the shorter lead is the negative. When I finish this amplifier, I've got some special music I'm going to play, and I'll just record it with the microphone on the camera. So I don't know how it'll sound, but it should sound pretty good. But I've got some special music I'm going to record that I don't have to worry about copyright. It's some royalty-free music, so we'll use that. And I can play you guys a couple songs when it's done, so you can actually listen to the sound quality off this thing. Even though you'll be hearing it through the microphone on the camera, it should still sound pretty good. C11 and C12 are 22 microfarad 350 volt capacitors, so we have to find the high voltage capacitors, which are in another bag here, and these are quite big because they are high voltage capacitors. So let's get our high voltage capacitors in here. Open up another bag of parts, put them all over the bench so I can lose them. 22 at 350. There's three of them, 11, 12, and 13. Here they are. And these are high temperature, 105 degree caps because they are in a switching power supply. See, 11, 12, and 13 go on the board in these spots here. 11, or 12, 11, and 13. So we'll just place them on the board. Paying attention, of course, to the polarity. And a word of caution to anybody planning on building one of these units. We are dealing with relatively high voltage on tube circuitry. So once this thing has been energized, these capacitors will hold a charge for can hold a charge for a long period of time, depending on the design of the circuit. I didn't look at the schematic closely to see whether this has got a bleed off circuit or not. Let's take a look at the schematic here to see whether the high voltage circuit has a bleed off on here. And it doesn't look like they have any bleed off voltage. So what that means in terms of safety on a unit like this, normally the idle current of the tube would pull the voltage down pretty quick when the amplifier has been operating. So if you've had the amplifier turned on and the tubes are up to operating temperature and you turn off the power, the cathode is still hot and there will be the idle current will discharge the filter capacitors by way of the primaries on the output transformers. However, saying that, if you were to turn the power on and then turn it off right away, the oscillator would start up, the high voltage transformer would start up, and it would charge up these capacitors. But if the vacuum tubes had not warmed up to operating temperature, there would be no current flow through the tubes to discharge these capacitors. So they would be sitting open circuit and could hold a charge for an extended period of time. We're talking hours, maybe even longer, because there's nothing to discharge them. So keep that in mind if you're working on one of these power supplies. After if there's a problem, for example, or if the tubes are removed, it's going to charge up and that voltage is going to stay there and it will not discharge. It'll be 220 volts DC. Probably not enough to kill you, but enough to give you a good jolt, that's for sure. But that's just a word of caution when working around any vacuum tube equipment. It is quite dangerous to work on. I have confidence working on vacuum tube equipment because when I took my apprenticeship started in the late 70s and into the early 80s, there was still an awful lot of vacuum tube TVs around. Tons of tube TVs, black and white and color. So I really got the good training on tubes. That's where I cut my teeth on tubes and then learned transistors after, because transistors were coming in, but there was still a lot of tube stuff out there. And besides building this little tube amplifier, I have 2 vintage radios that I'll be restoring on future videos just to keep you guys interested. Some really old stuff from going back to like the 1950s and 1960s. Anyway, we've got the these capacitors are now mounted. We have one more to mount to finish off item number 12, and that's a 2200 at 25 volt, which is going to be this big one here. It is C15, and I think you know where that goes. There's only one place big enough on the board to hold that one, and it's right there. This board is getting close to being populated. And then we can move over to the audio board. Next on the agenda is the audio output transformers. Here are the audio output transformers, each of them in its own little box to protect it. One of the most important components in a tube amp is the audio output transformer. That is going to make or break the sound, as it is the one component that is responsible for changing the high voltage, low current audio signal from the tube and turning it into a low voltage, high current signal for the speakers. Now you've got a primary and a secondary winding on here. The primary is 7K ohms and the secondary is 6 ohms. Now, I like to believe stickers, but I don't. Because if someone got the sticker on backwards, it would be wrong, right? It wouldn't work. So, we're going to get the meter out and we're just going to measure our winding and make sure that the 6 ohm side, which is this side here, is measuring. Well, it's actually measuring about 1 ohm, but that's good. And this is the other side, which is measuring about 600 ohms. So this is our primary. They call it 7K ohms, but that's on AC, not the DC load, which is going to be a lot lower. So now we have to mount these transformers down. They have tabs that we bend onto the board to hold it in place. Otherwise, the weight of the transformer would just cause the leads to get ripped out. So let's mount the two transformers. We'll carefully thread the primary and secondary wires through the board. And then we'll solder on our tabs and our wires. May be better to try and just twist the tabs, but because it's going to take a lot of heat, but I should be able to get some solder to flow here. There we go, that's good enough. This is just to hold the transformer down to the board. And then we can solder the wires on. And then we'll do the same for the other transformer on this side. So mounting the second transformer here, that now completes unit 1. Thing's actually quite heavy. So now we've checked off all the parts here, transformer 1 and 2. This board is completed. Now we can move on to the second board, but that's going to be in part 3. Join me for the building of the second board for this. Catch you in the next one. Bye for now.